NASA has just made a long-awaited and potentially game-changing decision. One of the most expensive pieces of the SLS has been scrapped, and ULA is stepping in with what looks like a much simpler replacement. At first glance, it seems like a brilliant fix, one that could finally make Artemis launches faster, cheaper, and far more practical. But there's a twist. Because even if this new system works perfectly, SpaceX's Starship could still end up replacing it. So what exactly changed, and why does it matter for the future of the Moon program? Find out everything in today's Tech Map episode. Finally, the day has come. NASA's Exploration Upper Stage, or EUS, has officially been decommissioned. Instead of continuing to fund a project widely criticized as wasteful and politically driven, NASA is switching to ULA's Centaur 5 upper stage for the Artemis 4 and Artemis 5 missions. This change was revealed in a procurement filing published on March 6th, and the implications are bigger than they might seem at first. Because with EUS gone, SLS Block 1B is effectively dead as well. That version of the rocket was originally supposed to debut on Artemis 3. Now Artemis 3 will fly using the Block 1 configuration with the ICPS upper stage, the same setup used on Artemis 1 and Artemis 2. NASA says this shift is part of a broader strategy to move toward a standardized near Block 1 SLS configuration, paired with a new upper stage that could support roughly 10-month launch intervals and potentially annual lunar missions starting in 2028. But make no mistake, the cancellation of the EUS is more than an administrative change. For many observers, it marks the end of one of the most controversial programs in modern NASA history. For over a decade, EUS was supposed to be the centerpiece of the SLS upgrade plan, enabling Orion to send larger payloads toward the Moon. Instead, critics say it became a classic example of pork barrel spending. Billions of dollars were poured into the program in large part because it supported jobs in states like Alabama, Mississippi, Texas, and Florida, where key SLS contractors operate. And the numbers tell the story. Congress initially allocated $85 million in 2016 for early development. Since then, the project has absorbed more than $3.5 billion. What makes that figure even more surprising is the technology involved. The stage relied on the RL-10 engine, a design that has been flying reliably for nearly 60 years. This wasn't experimental propulsion, it was well-established hardware. Yet after more than a decade of development, the stage still remained years away from flight readiness. Boeing's original contract to build EUS started at $962 million, but costs quickly ballooned far beyond that. And the spending didn't stop there. Because EUS was larger than the existing SLS configuration, NASA also had to build a new launch tower at Kennedy Space Center, known as Mobile Launcher 2. Originally estimated at $383 million, the tower's cost has now surged to over $2 billion. Add it all together, and the ecosystem built around EUS has consumed more than $5.5 billion. All while other options already existed, options that were cheaper, simpler, and in some cases already flying, like ULA's Centaur 5, or alternative engine systems such as Blue Origin's BE-3U. The situation only began to change recently, after NASA's new administrator, Jared Isaacman, took office and began asking some straightforward questions. Namely, why are billions being spent on a system designed largely to support the Lunar Gateway Station when that station doesn't directly help astronauts land on the Moon? That line of thinking ultimately led to this decision, and many analysts see the shift towards Centaur 5 as a far more practical path forward. Compared to Blue Origin's proposed alternative, Centaur 5 is smaller, simpler, and far easier to integrate with existing SLS infrastructure. Blue Origin's upper stage, for example, would likely be too tall to fit inside the vehicle assembly building when stacked on top of the SLS core stage. Solving that problem would require designing a shortened version of the stage, essentially creating an entirely new variant that has never flown before. Centaur 5, on the other hand, fits neatly within NASA's existing systems. It also avoids major modifications to Mobile Launcher 1. Blue Origin's concept would require moving the upper stage access arm, relocating Orion umbilicals, modifying the crew access arm, and building new ground support equipment for BE-3U engines and subcooled liquid oxygen systems. Those upgrades alone could cost hundreds of millions of dollars. Centaur 5 requires only minor adjustments to existing umbilicals, and it already works with the liquid hydrogen and liquid oxygen systems at Kennedy Space Center. But perhaps the biggest advantage is something engineers like to call engineering DNA. Centaur 5 shares a lot of heritage with hardware NASA already understands. It uses the same RL-10 engine family, similar avionics systems, and a flight termination system closely related to what already flies on the ICPS. That means qualification could happen much faster, with far fewer unknowns. Fuel compatibility is another major benefit. Blue Origin's system uses subcooled liquid oxygen, which operates at different temperatures than the standard propellants used by the SLS core stage. Centaur 5, however, uses the same propellant combinations already handled by SLS ground systems. By relying on proven hardware and minimizing new infrastructure, NASA could finally make more frequent Artemis launches possible, potentially even annual missions to the Moon. And if that happens, the Artemis program could remain operational well into the mid-2030s. For nearly 2 decades, Orion and the SLS have essentially been inseparable. The spacecraft was designed specifically to fly on SLS, and the entire Artemis architecture has been built around that pairing. But that relationship may not stay exclusive forever, because Lockheed Martin is now exploring a very different business model for Orion. Historically, NASA used what's called a cost-plus contract. Under that system, NASA pays contractors to build hardware, closely supervises the development process, and then takes direct operational control once the spacecraft is delivered. The new idea flips that model. Instead of simply delivering a vehicle, Lockheed Martin would provide Orion as a full service. That means handling everything from ground preparation to launch integration, orbital operations, docking, and ultimately, bringing the crew safely back to Earth. In other words, Orion becomes a commercial service, not just a government-owned spacecraft. And that opens the door to something that once seemed almost impossible: launching Orion on rockets that are not the SLS. To compete on price, Lockheed has already begun studying the possibility of flying Orion on commercial heavy-lift vehicles, like Falcon Heavy or Blue Origin's New Glenn. But there's another piece of the puzzle that makes this possible. Lockheed says reusing Orion hardware will be critically important for making this service model affordable. The company plans to build a fleet of 3 largely reusable Orion spacecraft. Those vehicles would debut sequentially on Artemis 3, 4, and 5, and then continue flying on later missions after refurbishment. If that plan works, the cost savings could be significant. Locked's goal is to reduce the production cost of the Orion spacecraft by about 50% between Artemis 2 and Artemis 5. And after that, improved refurbishment processes could push costs down by another 30% or more. At this point, some people are starting to ask an obvious question. If SLS becomes more standardized and Orion becomes more reusable, could NASA eventually reduce its reliance on SpaceX? After all, the agency has traditionally preferred proven, government-controlled hardware whenever possible. But the reality may be a bit more complicated than that. Because in some scenarios, NASA's reliance on SpaceX could actually increase. For example, if Lockheed Martin decides to launch Orion on Falcon Heavy to save money, NASA would still be depending on SpaceX launch hardware. At the same time, NASA's plan to standardize the Near Block 1 SLS configuration is meant to support launch intervals of roughly every 10 months. This internal capability ensures the agency has a proven alternative to SpaceX's Starship system for heavy-lift lunar logistics. But then there's Starship, and Starship plays by an entirely different set of rules. Elon Musk's goal is not just annual launches, it's dozens of launches per year, eventually far more than that. And thanks to full reusability, the long-term cost per launch could be dramatically lower. Payload capability is another major factor. Starship is expected to deliver over 100 tons to lunar orbit. That completely dwarfs the capability of SLS, even with the now cancelled exploration upper stage. In practical terms, that means a single Starship flight could potentially deliver entire lunar landers or large cargo modules, while SLS and Orion are primarily focused on transporting astronauts. So while SLS standardization improves cadence and cost control, it doesn't really close the payload gap. Because of that, many analysts believe that Starship, or possibly a future New Glenn variant, could eventually replace SLS entirely. But that transition probably won't happen overnight. Most projections suggest that SLS will remain essential for the early Artemis missions throughout the late 2020s. The real turning point likely arrives sometime in the 2030s, once commercial heavy-lift systems have demonstrated consistent reliability. And that brings us to an interesting interpretation of NASA's recent decision. Some critics have described the cancellation of the EUS as the beginning of a death crawl for the SLS program. Without EUS, and without the massive Mobile Launcher 2 tower that supported it, SLS will no longer receive the huge upgrades originally planned, which naturally raises questions about its long-term future in a fiercely competitive environment with modern, low-cost rockets. But NASA's current leadership seems to be taking a more strategic approach. Instead of abruptly canceling SLS, the agency appears to be stabilizing and simplifying the system. In other words, fewer custom parts, fewer delays, and far less money spent on infrastructure. This approach helps NASA retain options. If the SLS/Orion really has to stop after Artemis 4, 5, or 6, then the transition to SpaceX technology will also take place in a context where NASA has saved billions of dollars by cutting back on boondoggle projects like EUS. In a way, Jared Isaacman's strategy seems designed to prepare for exactly that scenario.
It might seem like in the age of AI, everything will eventually be fully automated. But in reality, there's still a pretty intense debate happening between traditional aerospace thinking and the technologies that are shaping the future. And right now, that debate is playing out between NASA and SpaceX, specifically over how astronauts will manually control Starship HLS during a lunar landing. NASA believes SpaceX's current approach doesn't fully meet the agency's requirements in an emergency. Now, NASA's human rating rules are very clear about this. Any spacecraft carrying astronauts must allow the crew to manually control the vehicle's flight path and attitude if needed. Think of something similar to the Apollo lander's actual pilot authority during critical moments. And this isn't just a guideline. It's written directly into the Human Landing System contract that SpaceX won. Starship HLS has to meet this requirement before astronauts can ever board the vehicle. But here's where things get interesting. SpaceX actually agrees with the requirement for manual control. The difference is how they define it. Instead of traditional joystick-style piloting, SpaceX proposes a system built around fly-by-wire control. In this setup, astronauts don't directly command every engine or thruster. Instead, they give high-level inputs, things like move left, slow down, or target that landing spot. From there, onboard flight computers translate those commands into thousands of precise adjustments every second. The system automatically controls the Raptor engine's flaps and reaction control thrusters to execute the maneuver safely. In other words, astronauts still make the decisions, but the computer handles the extremely complex physics of flying the vehicle. And that actually includes emergency situations as well. If something goes wrong, the crew could select a new landing site or trigger an abort command. The computer would then calculate the safest trajectory, check fuel margins, and warn the crew if the maneuver isn't possible. So the astronaut essentially points to where they want to go, and the system figures out how to get there safely. If that sounds familiar, it's because systems like this are already widely used in aviation. Many Airbus aircraft, for example, use fly-by-wire controls. Pilots still fly the airplane, but their inputs pass through a computer that constantly calculates the safest control movements and keeps the aircraft within a safe flight envelope. Even in emergencies, pilots rarely control every surface directly. The computer is always helping stabilize the aircraft. But NASA appears to view SpaceX's approach differently. According to the agency, simply selecting a landing location on a screen while the computer performs the maneuver does not fully qualify as manual control. NASA wants astronauts to retain the ability to directly fly the vehicle if the automated systems fail, especially during critical phases like the final descent, avoiding obstacles, or adjusting course near the lunar surface. Exactly what that means for Starship's cockpit is still unclear. Some have wondered whether NASA might require physical joysticks similar to those used on Crew Dragon. But realistically, manually piloting Starship in the traditional sense would be extremely difficult. Starship's lunar landing profile demands split-second precision. The vehicle must transition from a high-speed descent to a controlled landing while managing multiple powerful engines, dust plumes, and uneven terrain. This is a system making thousands of adjustments every second, far faster than any human pilot could react. Trying to control that manually would be somewhat like attempting to land a commercial airliner in a storm while blindfolded. Computers are simply much better at calculating the exact timing needed for complex maneuvers, like a hover slam landing. Something SpaceX has already demonstrated hundreds of times with its rockets. In fact, some experts describe Starship's landing dynamics as similar to balancing a double inverted pendulum, an extremely unstable configuration that would be nearly impossible for humans to control without software assistance. And then there's the scale of the vehicle itself. The Apollo lunar lander stood about 7 meters tall and weighed roughly 16 tons. Starship, by comparison, is a completely different class of machine, around 70 meters tall, and potentially 300 tons on the lunar surface. Controlling something that large requires extraordinary precision. Because of that, most experts believe that even if NASA insists on manual backup control, it will likely still rely on fly-by-wire assistance. Astronauts would command the maneuver while computers execute the detailed control movements. Direct mechanical piloting, like in older spacecraft, simply isn't practical for a vehicle this complex. That said, Starship HLS is still expected to include a traditional cockpit layout to support astronauts during lunar operations. This would likely include outward-facing windows, along with a variety of digital displays, camera feeds, and vision assistance systems. And those vision systems will be especially important. Because the Starship cockpit sits roughly 40 meters above the lunar surface, actually seeing the landing zone through a window would be extremely difficult. So astronauts will probably rely on several advanced tools. One of them is synthetic vision, which combines images from cameras mounted underneath the spacecraft to create a real-time view as if the pilot were sitting close to the ground. Another possibility is a helmet-mounted display system similar to what F-35 fighter pilots use. With that technology, astronauts could effectively see through the spacecraft using camera data projected directly into their visors. And finally, a head-up display would place key information like altitude velocity and landing guidance directly in the astronaut's field of view. So in many ways, Starship's landing system would combine human decision-making with powerful onboard automation. Which brings up an interesting question. What kind of control would you prefer for the first lunar Starship landing? A more traditional system, where astronauts directly pilot the vehicle, or SpaceX's approach, where astronauts give commands, and the computer handles the complex physics. Let me know what you think in the comments below. And of course, if you enjoyed this breakdown, don't forget to like, share, and subscribe so you don't miss future updates on Starship Artemis and the future of space exploration. However, from NASA's perspective, The demand for an additional layer of human control is actually quite reasonable, and there's a serious reason behind that. According to NASA's internal safety assessments, lunar landers represent the highest risk of crew loss anywhere in the entire Artemis program. Unlike missions in low Earth orbit, there is currently no astronaut rescue option on the Moon. If something goes wrong on the lunar surface, there's no backup spacecraft coming to pick up the crew. The only real strategy is to make sure a catastrophic failure never happens in the first place. That's why NASA tends to favor systems where astronauts can directly intervene if something unexpected occurs. And when they make that argument, they often point to the Apollo missions as the clearest example of why human control still matters. All 6 Apollo lunar landings required manual control in the final descent stage. But here's where the debate becomes complicated. The logic that made sense in 1969 doesn't translate perfectly to a vehicle like Starship HLS. Starship isn't just another lunar lander. It's an enormous and extremely complex spacecraft, unlike anything that has ever attempted a lunar landing before. Its sheer scale changes the engineering challenges dramatically. There's also another important factor: modern computing technology. The computers used during the Apollo program were remarkable for their time, but they were extremely limited compared to today's systems. They lacked modern sensors, real-time terrain mapping, and advanced navigation tools. Issues like navigation drift or mismatched landmarks were almost inevitable. Starship's software environment is fundamentally different. The vehicle is expected to rely on modern computing architectures, advanced sensors, and powerful onboard processing, potentially combining technologies like LiDAR radar mapping and sophisticated flight algorithms to understand its surroundings in real time. In theory, systems like these could automatically handle many of the situations that Apollo astronauts had to solve manually. But NASA still sees a major concern: Starship hasn't proven itself yet. From the agency's perspective, this actually makes the situation even more challenging than the debates they had with SpaceX a decade ago during the development of Crew Dragon. By then, SpaceX and NASA also had a disagreement regarding how the spacecraft should be piloted. SpaceX aimed for a highly automated system that relied exclusively on touchscreens, offering astronauts only a limited set of flight commands. NASA pushed back against this minimalist approach, requesting traditional joysticks so that astronauts could fly the Crew Dragon in a manner similar to previous human-rated spacecraft. The stalemate was broken by Garrett Reisman, a former NASA astronaut who was working for SpaceX at the time. He helped broker a compromise where the vehicle could indeed be flown manually, but instead of using physical sticks, the manual controls were integrated into the touchscreen interface. A critical reason this compromise was successful was that the flight controls for the Crew Dragon were built upon the proven flight heritage of the cargo version of the Dragon. This is what Starship lacks. Dragon had already completed numerous successful missions to the International Space Station, providing a level of reliability that NASA found acceptable for the transition to crewed flight. For months, there was a proposal circulating in Congress that would place a 50% cap on NASA's launch procurement funding for any single company. In simple terms, NASA would not be allowed to spend more than half of its launch budget with one provider, no matter how capable or reliable that provider might be. But in the final version of the NASA reauthorization bill, that provision was removed. And for many in the space industry, that outcome was a major relief. At first glance, the cap sounds reasonable. Promote competition. Strengthen the industrial base. Avoid dependency. But here's the reality. SpaceX currently handles a massive share of NASA's launch portfolio. Crew rotations to the ISS with Dragon, cargo missions, high-priority science payloads, and of course the human landing system contract for Artemis. If this law passes, it could directly limit NASA's ability to continue awarding major missions to SpaceX, including future crewed lunar missions. And among the supporters of this legislation, Jim Bridenstine, now working as a lobbyist for ULA, one of SpaceX's primary competitors. On LinkedIn, he wrote, "I'm encouraged to see Congress taking meaningful steps to strengthen the industrial base that underpins both our civil and national security space missions." That's a very different tone from 2020. Do you remember Demo 2? When Crew Dragon successfully launched American astronauts from American soil for the first time since shuttle retirement, Bridenstine stood there and declared,
"We are launching a new era in human spaceflight."
At the time, it felt like alignment. NASA and SpaceX are pushing in the same direction, but fast forward to today, and the posture has shifted. And this isn't the first sign. Last year, Bridenstine publicly criticized NASA's decision to choose Starship as the lunar lander, saying,
The biggest decision in the history of NASA, at least since I've been paying attention, the biggest decision happened in the absence of a NASA administrator, and that decision was, instead of buying a moon lander, we're going to buy a big rocket.
That's a striking statement, because here's the contradiction. Bridenstine was one of the architects of the Artemis framework that led to SpaceX's selection in the first place. Under his leadership, NASA selected SpaceX's Starship as one of 3 finalists for the HLS contract. He appointed Kathy Lueders to lead NASA's Human Exploration Division, and it was Lueders who ultimately awarded SpaceX the sole contract, largely because their bid aligned with the budget constraints Bridenstine had negotiated with Congress. In other words, the process that resulted in Starship winning, it was built on his watch. Which makes this moment feel unusual. It's one thing to evolve your position as new information emerges. That's normal in policy. But this feels different. It feels like he's challenging the very structure he helped create. And the reaction from the space community? It wasn't subtle. It was intense disappointment. Right now, SpaceX is not dominant because NASA locked everyone else out. Quite the opposite. Multiple providers received major contracts over the past decade. Some delivered, some didn't. SpaceX did repeatedly. So is Bridenstine unaware of that reality? Highly unlikely. As a former NASA boss, he understands the procurement landscape better than almost anyone. Which is why some observers think this isn't about misunderstanding at all. One commenter summed up that theory bluntly. I'm pretty disappointed that this is where Bridenstine has ended up, but maybe he just views things like I do my best to advocate for my employer. When that was NASA, he pursued NASA's interests now. It's basically ULA, so he's shilling full on for ULA. Bridenstine served in NASA from April 2018 to January 2021. During that time, SpaceX's historic Crew Dragon Demo 2 event took place. That moment wasn't just historic for NASA. It significantly elevated Bridenstine's reputation. He was the administrator who brought human launches back to American soil. He left NASA in January 2021. 3 months later, he joined Viasat's board of directors, a direct competitor to Starlink. Later, he became executive director of government operations at ULA, one of SpaceX's biggest launch competitors. In 2025 alone, his consulting firm, the Artemis Group, earned $990,000 from ULA, SpaceX's competitor, in 2025 alone. This figure accounts for nearly a third of his total lobbying revenue last year. This has led the community to believe that his statements about competition are merely a cover for vested interests. Critics argue that the proposed 50% funding cap isn't just controversial, it's structurally flawed. Let's walk through the scenarios people are highlighting. First scenario, the single launch problem. Imagine NASA only contracts one payload launch in a given year. How do you pay a launch provider for one mission while ensuring no provider receives more than 50% of total launch funding that year? Even if there are 2 launches, they're never identical. One might go to low Earth orbit. Another might go to a high-energy trajectory significantly more expensive. If Launch A costs $101 and Launch B costs $99, the provider for Launch A has received 50.5% of the funding. Technically, over the limit. Now, procurement isn't about picking the best rocket for the mission. It becomes an accounting puzzle. Companies would have to bid artificially adjusted numbers just to satisfy percentage caps. That's not market competition, that's spreadsheet engineering. Third scenario. The hostage bid scenario. This is where it gets really strange. Suppose 3 launches are scheduled in a year. 3 companies are capable of delivering them. SpaceX and Blue Origin have already reached their 50% thresholds. That leaves one company legally allowed to bid on the next mission. If they know they're the only eligible bidder, what incentive do they have to keep prices low? They could bid $1 billion for a mission that normally costs $100 million. NASA would be forced to either overpay or cancel the mission entirely. That's not increasing competition. That's eliminating it. Fourth scenario, the lumpy budget reality. NASA doesn't launch identical missions every month like a shipping company. Its manifest is irregular. Some years include massive flagship missions, a Mars rover, a space telescope that happen once a decade. If one mission costs $300 million to launch, and 5 smaller missions cost $20 million each, the provider of that flagship mission automatically exceeds the 50% threshold. The space agency might be forced to delay major scientific projects simply to wait for the accounting year to reset. Then came one of the strongest pushbacks yet from inside the House. Former NASA official Phil McAllister didn't mince words. He called the legislation exactly what he believes it is, anti-competitive. And he explained why that part of the legislation does not support competition. What it supports is using the political process to funnel money to favored companies with inferior products. Competition is a full and open match between companies where the best company wins. That's not subtle. That's a direct challenge to the premise of the bill. But he didn't stop there. He laid out what he believes would actually happen if this passes in its current form. It ensures that the best company will not win. Instead, the second or third place company will get an award because they could not compete and win fairly. And the biggest loser in all this is America and the American taxpayer, because our space agency NASA will be forced to pay more for inferior products. And yes, there's an uncomfortable irony here. For companies like Boeing or ULA, which have struggled for years to match SpaceX's reusability and launch cadence, this could look less like competition and more like a consolation prize. Now, beyond politics and rivalry, there's a more practical concern capability. Right now, when it comes to NASA's highest-risk, highest-value missions, only 2 rockets have Category 3 certification, Falcon 9 and Falcon Heavy. That certification allows them to launch billion-dollar high-consequence payloads. Competitors like ULA's Vulcan and Blue Origin's New Glenn have not yet demonstrated that same level of reliability. ULA has faced challenges with Vulcan development and has had to shift certain missions because it couldn't meet commitments on time. Meanwhile, SpaceX is launching every few days, so critics ask if one provider is operational at scale and others are still ramping up. What happens when you force NASA to distribute funding evenly. Some see it as NASA shooting itself in the foot. McAllister framed it even more bluntly, and the industrial base will be weakened, not strengthened, because lower-grade suppliers will be protected from competition. And the country will see that superior performance does not win, having the best lobbyist does.
As Flight 12 approaches, we're already seeing a major step toward the next generation of Starship. The first version 3 vehicle, S-39, has left the build site and begun its pre-launch testing campaign. As of this recording, it's at Massey undergoing cryogenic tests, and reportedly, the first 3 major tests have gone smoothly. That alone would be notable. But what really caught attention was a comment from Elon Musk, who said he is highly confident that the version 3 design will achieve full reusability. Now, if that actually happens, it wouldn't come entirely out of nowhere. SpaceX has already demonstrated one half of the equation, catching the Super Heavy booster. The first successful catch happened during Flight 5 back on October 13, 2024, and since then, they've repeated the maneuver several times, including Flights 7 and 8. The ship itself, however, is a different story. Musk first raised the idea of catching the Starship upper stage with the tower's chopsticks back in early 2025, but the debut of version 2 and its 3 explosions in early 2025 pushed that timeline back. And honestly, that's not surprising. Catching the ship is much harder than catching the booster. The booster follows a predictable suborbital return using grid fins to guide itself home. Starship, by contrast, must survive full orbital re-entry, endure extreme heating, and then execute a precise landing maneuver at the end. The tower alignment is tighter, and the vehicle needs far more complex attitude control to line up with the catch arms. So the fact that booster catches worked after only a handful of flights doesn't necessarily translate to the ship. But now things are starting to look different. After flying Block 2 starships up to 5 times and gathering a huge amount of real flight data, SpaceX is moving into the Block 3 generation, and according to Musk, this is the version designed to finally make full reusability possible, meaning both the booster and the ship returning to the tower. SpaceX says those years of flight testing have now been folded directly into the hardware. Block 3 includes a number of structural and system upgrades that are specifically aimed at solving the biggest reusability challenges seen in earlier vehicles. So the question is, how exactly are they planning to do that? Well, the first place to look is the engine. The transition to the Raptor 3 is probably the single most important change in the entire vehicle. Yuan described it as the shift from a complicated prototype engine to something much closer to a robust production system. Musk says one of the biggest improvements is something surprisingly simple: much less extra mass. And he's not talking about the core engine itself. Most of that excess weight comes from everything attached to it: pipes, mounts, sensors, cooling lines, shielding, valves, and all the hardware needed to connect the engine to Starship or the Super Heavy booster. The new design simplifies a lot of that. For example, integrated regenerative cooling channels replace the large external shielding that earlier Raptors needed. That alone cuts about 550 kilograms of mass per engine, bringing the total engine mass down to roughly 1.525 tons, compared to about 1.63 to over 2 tons for Raptor 2. At the same time, those internal cooling channels allow the engine to operate at higher chamber pressures for longer periods without overheating or requiring heavy refurbishment after flight. SpaceX has also simplified the plumbing. Many of the external lines are now integrated directly into the pumps and the engine structure itself. That means fewer parts, fewer welds, and far fewer potential failure points during the intense vibrations of launch and re-entry. And Musk says this isn't even the end of the road. Future variants, possibly something like Raptor 3X, could remove even more of that supporting hardware and push the engine's mass even lower. Performance is improving as well. Chamber pressure is expected to reach around 350 bar, up from roughly 300 bar on Raptor 2, allowing the full-flow staged combustion cycle to run efficiently without overstressing the turbines. Thrust is increasing too. Raptor version 3 is expected to produce about 280 tons of thrust, compared to roughly 230 tons for Raptor 2, with a specific impulse near 350 seconds. That puts the thrust-to-weight ratio close to 200 to 1, making it one of the most powerful engines relative to its mass ever built. More importantly, it gives both the booster and the ship extra margin for re-entry and landing burns, even with heavy fuel loads. For a long time, the heat shield has been widely considered the biggest elephant in the room. And the reason is simple. Earlier Starship flights showed just how difficult this problem really is. On Block 1 and Block 2 vehicles, the thermal protection tiles occasionally suffered losses during flight. Some were shaken loose by vibration, others were affected by oxidation, and in a few cases, small cooling leaks created additional stress on the tile system. Block 3 appears to be SpaceX's most serious attempt yet to solve that problem. The windward side of the vehicle, the side that faces the plasma during re-entry, now has almost continuous hexagonal tile coverage. Earlier versions had small, exposed steel regions that could become vulnerable under extreme heating. Those gaps are now largely gone, thanks to a tighter tile layout. There is also an invention, something called a crunch wrap material that seals the tiny gaps between tiles. This blocks hot plasma intrusion during re-entry, preventing heat leakage to the underlying ablative layers and steel structure. But the upgrade isn't just about adding more tiles. Underneath them, SpaceX has introduced additional protective layers. A secondary ablative layer sits beneath the tiles. The idea is to act as a backup barrier if a tile is damaged or lost during flight. The tiles themselves have also changed. They now appear darker, with a deeper black and slightly glossy finish. That new composition is designed to improve thermal management, resist fatigue, and maintain uniform performance at temperatures that can exceed 1,400 to 1,600 degrees Celsius during re-entry. But solving the heat shield isn't just about the tiles. Aerodynamics plays a huge role as well. One of the most noticeable changes on Block 3 involves the forward flaps. These control surfaces have been moved slightly leeward, meaning farther back toward the less exposed side of the vehicle. That repositioning helps protect the flap hinges from the direct plasma flow, something that caused issues on earlier flights. Those adjustments also reduce drag exposure and limit the amount of plasma hitting the leading edges. In practical terms, that means less heating, less tile stress, and less ablation during re-entry, all of which help improve the odds of rapid reuse. Another major design change shows up in the hot staging system. On earlier versions of Starship, the stage separation hardware existed as a largely separate structure. But on Block 3, the hot staging ring is now fully integrated into the spacecraft's body. You can actually see this visually in the structure. It forms a distinctive zigzagging network of open struts, with larger vents that allow engine exhaust to escape more freely during staging. That change directly addresses problems seen on previous flights, where exhaust back pressure interfered with the ship's engines during the hot staging process. And inside that structure is one of the most interesting design features of the entire vehicle: the segmented dome. This dome performs what is essentially a dual role. First, it serves as the top of the liquid methane tank. But at the same time, it also acts as the structural element that absorbs heat and thrust when Starship's engines ignite while the ship is still attached to the booster. By combining those functions into a single component, SpaceX eliminates additional structures, reduces mass, and frees up more internal volume for propellant. But if the goal is rapid reusability, the ship also needs to be recovered quickly after landing. For that reason, Block 3 includes reinforced structural sections specifically designed to handle the compressive loads from Mechazilla's catch arms. When the tower grabs the ship, those arms apply enormous squeezing forces, so the structure needs to be prepared for it. At the same time, the vehicle itself has grown significantly. The Block 3 ship is expected to be around 70 meters tall, compared to roughly 50 meters for Block 2, and it carries much more propellant, roughly 2,300 tons instead of about 1,500 tons. That additional propellant provides more margin for the most delicate part of the mission, the final landing burn and tower catch maneuver. But Musk's confidence in full reusability isn't just about a single vehicle design. It's about the entire production system behind it. Block 3 ships are being built inside SpaceX's new Star Factory, where standardized jigs enable precise, repeatable positioning for welding stainless steel rings, reducing complexity from custom fits in earlier blocks. At the same time, the quick disconnect systems for propellant, power, and data have been overhauled from earlier versions' rigid, hydraulically actuated arms to more automated, plug-and-play designs. The goal is to make pad operations faster and reduce turnaround time between launches. Still, even with all of these upgrades, SpaceX is not rushing directly into a tower catch for the ship. Musk has outlined a fairly strict safety rule for that final step. Before attempting a catch with Mechazilla, Starship must complete 2 perfect soft landings in the ocean. This 2 landing rule allows engineers to confirm that the heat shield, guidance system, and landing burn all work reliably. Only after those flights demonstrate consistent performance will SpaceX attempt to recover the ship directly at the launch tower. The idea is straightforward. Reduce the chances of a vehicle failure near the launch site before attempting the most complex recovery maneuver in the entire system. For more than a decade now, space enthusiasts have been asking the same uncomfortable question. How did Apollo go from a blank sheet of paper to footprints on the moon in just 8 years, while Artemis, announced in 2011, still hasn't returned a single astronaut beyond low Earth orbit? The difference begins with urgency. At its peak, Apollo consumed 4.4% of the U.S. federal budget. Fueled by Cold War rivalry and national prestige, Congress opened the funding floodgates. Speed was the mission. Artemis operates in a different era. NASA now receives a fraction of that support, constrained by political gridlock and competing priorities. Instead of a tightly integrated program, Artemis has evolved into a sprawling network of contractors across 29 states, slower, more complex, and structurally heavier. The hardware reflects that reality. SLS repurposes Space Shuttle-era technology, requiring costly modernization. Orion has faced delays of its own, but funding and legacy systems are only part of the problem. The deeper challenge is architectural complexity. Unlike Apollo's unified design, Artemis depends on multiple giants: Boeing's SLS, Lockheed's Orion, SpaceX's Starship lander, and Blue Origin's alternative, all required to operate in perfect sequence. Nowhere was this risk clearer than in the original Artemis III plan, which attempted 3 firsts at once: a crewed Starship flight, large-scale orbital refueling, and a lunar landing. Any one would be ambitious. Together, they turned the mission into a gamble. Starship's refueling system remains unproven at scale. Multi-company docking adds risk. One leak, one glitch, one failure in the chain, and as delays mounted, headlines shifted from anticipation to concern, especially as China's lunar ambitions accelerated. The question is no longer just when America returns to the moon. It's whether it can do so fast enough. That mounting pressure forced a rethink, and that rethink began with Artemis III. The timeline of 2027 remains, but the mission itself has changed dramatically. Instead of attempting a lunar landing on its first try, Artemis III will now serve as a proving ground in low Earth orbit. The human landing system will launch uncrewed and rendezvous with a crewed Orion capsule. Rather than a one-shot moon attempt, the mission will focus on docking demonstrations, systems validation, and operational rehearsals. It is no longer SpaceX's solo performance. Astronauts will evaluate lander systems from multiple partners, whether SpaceX's Starship, Blue Origin's Blue Moon, or potentially both. Inside Orion, the crew will also test next-generation lunar spacesuits in the vacuum of space. If this sounds familiar, it should. In 1969, Apollo 9 tested the lunar module in Earth orbit before committing to a lunar landing. It was a dress rehearsal, a controlled environment to uncover flaws before the stakes became existential. Artemis III now mirrors that philosophy. Rather than betting everything on an unproven stack, NASA is decomposing the risk. Learn in orbit. Validate systems. Identify weaknesses. Then proceed. The actual lunar landing has shifted to Artemis IV, currently targeted for 2028. And notably, the specific lander for that mission has not yet been finalized. Performance during Artemis III will play a decisive role in determining which system earns the responsibility of carrying astronauts down to the lunar surface. Quietly, beneath the official press releases and congressional hearings, a different kind of race is unfolding. On one side stands Elon Musk's SpaceX, with its towering Starship HLS. On the other, Jeff Bezos's Blue Origin, developing the Blue Moon Mark II. Both are competing for the same prize: to carry American astronauts back to the lunar surface. For the space community, Starship HLS needs little introduction. It is colossal. Standing over 50 meters tall with a 9-meter diameter, it dwarfs Apollo's lunar module. It runs on methane-fueled Raptor engines, a propellant choice designed for reusability and future Mars missions. And on paper, it is staggering. More than 100 tons of payload capacity to the lunar surface, enough for crews of 4, habitats, rovers, and the beginnings of a permanent base. Blue Origin's Blue Moon Mark II takes a very different approach. At roughly 15 meters tall, it is far more compact, narrower, more specialized. Its payload capacity is closer to 20 tons, about 1/5 of Starship's. That might sound like a disadvantage, but it reflects a different philosophy. Mark II isn't designed to brute force a lunar base into existence. It is optimized for precision operations and gateway docking. Instead of methane, it uses hydrogen-oxygen BE-7 engines. 2 landers, 2 radically different visions of how to return to the moon. But the real contrast appears not on the surface, it appears in orbit. Starship requires orbital refueling. After launch, it must be topped off by a fleet of dedicated tanker starships in low Earth orbit before heading toward the moon. Estimates suggest anywhere from 10 to 20 tanker flights may be required to transfer more than 1,200 tons of super-cold methylox propellant. Blue Origin's solution is arguably even more elaborate. Instead of tanker versions of the same vehicle, Blue Moon relies on something called the cislunar transporter. It consists of 2 major components: a tug equipped with 3 BE-7 engines and a tanker module for carrying propellant. These pieces launch separately aboard New Glenn rockets and assemble in Earth orbit, snapping together like orbital Lego bricks. Then it gets more intricate. Additional New Glenn rockets launch upper stages carrying residual propellant. The assembled transporter docks with those stages and siphons off their leftover fuel. Once filled, it travels to a near-rectilinear halo orbit around the Moon, the same orbit planned for the Gateway Station, where it refuels the Blue Moon lander. Compared to Starship's direct tanker-to-lander approach, Blue Origin's method requires more launches and more assembly steps. Starship makes everything simple, but simplicity does not mean easy. Starship's greatest strength, its sheer size, is also its greatest engineering burden. Moving over 1,000 tons of cryogenic methane and oxygen in orbit has never been demonstrated at this scale. Methane, while easier to handle than hydrogen in some respects, still presents boil-off challenges. Raptor engines must remain stable after long-duration cryogenic exposure. Docking systems must operate repeatedly without failure. And then there's Starship Block 3, the variant expected to support Artemis. As of now, it has not flown. That means many of the systems required for Artemis remain untested in real mission conditions. With Artemis 3 targeting 2027, time is measurable. That reality has placed enormous pressure on SpaceX teams in Texas and California. But paradoxically, NASA's recent restructuring of Artemis 3 may have given them breathing room. Under the revised plan, the most daunting challenge, large-scale orbital refueling for a lunar mission, is temporarily removed from the critical path. The LEO demonstration can be achieved with far fewer launches, no lunar descent engines, no landing legs, no surface operations. Just the fundamentals: life support, docking, crew safety. That said, few expect SpaceX to sit idle. A ship-to-ship propellant transfer demo in late 2026 would align perfectly with their philosophy. They need data. They need failure points. They need iteration cycles, because that is how SpaceX operates. In late 2025, The company formally proposed what it called a simplified mission architecture to NASA. The recent Artemis redesign strongly resembles that proposal. It allows SpaceX to focus on what it already does well: rapid prototyping, frequent launches, and iterative testing in low Earth orbit before tackling the uniquely hostile conditions of the lunar South Pole. This aligns with Musk's core engineering mantra: test to failure. SpaceX does not aim for flawless first attempts. It flies early, breaks things, fixes them, flies again. Apollo, in many ways, followed a similar incremental ladder of missions, each building toward the next. A restructured Artemis 3 gives Starship something it desperately needs: the chance to prove itself in stages rather than all at once. Not perfection or bust, but progress through iteration. So how close is SpaceX to being ready? Closer than it may seem. Behind the spectacle of test flights, SpaceX has been steadily clearing critical milestones for Starship HLS. In February 2024, the company completed full testing of its environmental control and life support system, the hardware that will keep astronauts alive. That same month, NASA validated full-scale docking tests between Starship HLS and Orion, later extending to gateway configurations. More than 30 Artemis-specific milestones have now been completed, spanning power, communications, propulsion, navigation, and space environment protection. Then came a key breakthrough on March 14, 2024. During Integrated Flight Test 3, SpaceX successfully demonstrated in-flight cryogenic propellant transfer inside Starship, an essential precursor to the far more complex orbital refueling campaigns required for a lunar mission. Now attention shifts to Block 3, the configuration expected to carry the Artemis burden. SpaceX is targeting its debut around Flight 12, currently tracking toward March. Hardware preparation is already underway. Ship 39 and Booster 19 are leading that charge. On February 26th, after months inside Mega Bay 2, Ship 39 rolled out, notably without engines, to undergo cryogenic proof testing. Upcoming tests will go further: forward and aft flap validation, structural squeeze tests using chopstick simulators, replicating the mechanical loads from the launch tower arms that catch returning boosters. Every interface, every stress point is being pushed deliberately. Once complete, Ship 39 will return to the production site for engine installation before rolling back out for static fire testing. Only then does it approach flight readiness. Meanwhile, Booster 19 has already completed a rigorous pre-flight test campaign. Multiple full cryogenic proof cycles were conducted, a direct response to issues that led to the loss of Booster 18. The lessons learned were not theoretical, they were structural.
In space exploration, safety is always the top priority. It's not just about sending astronauts into orbit and bringing them home at the end of a mission. NASA also has to plan for emergencies that might happen while crews are still in space. Because of this, NASA began considering a dedicated emergency return vehicle decades ago. The idea was simple: if astronauts ever had to evacuate the ISS due to a fire, toxic leak, or structural problem, they would need a fast and reliable way to return to Earth. After the 1986 Challenger disaster, NASA and partners, such as the European Space Agency, began developing a system called the Crew Return Vehicle, also known as the Assured Crew Return Vehicle. Its prototype, the X-38, was designed to act as a permanent lifeboat for the ISS. It would remain docked at the station at all times, ready to carry astronauts back to Earth in an emergency, without relying on Russia's Soyuz spacecraft, which was then the station's only escape option. For a time, the project made significant progress. NASA conducted successful drop tests of atmospheric prototypes, and an orbital test vehicle was reportedly 80 to 90% complete. However, the program eventually ran into a familiar obstacle: rising costs. The X-38's budget grew from about $96 million to $124 million, while the total Crew Return Vehicle program was projected to exceed $1.1 billion. Facing broader financial pressures from the ISS program, NASA conducted a cost review that recommended cutting non-essential systems. As a result, the Crew Return Vehicle was canceled in April 2002. After more than 7 years of development and roughly $1.5 billion spent, the dedicated ISS lifeboat never reached space. Its cancellation left the station increasingly reliant on Russia's Soyuz spacecraft for both crew transport and emergency evacuation. While Soyuz worked reliably, it also had limitations. Reliance on a Russian vehicle raised potential political concerns during periods of international tension. But that situation changed dramatically in 2020 when SpaceX's Crew Dragon spacecraft successfully flew its Demo 2 mission, carrying NASA astronauts to the station for the first time. Suddenly, the United States once again had its own human-rated spacecraft capable of transporting astronauts to and from orbit. And just as importantly, it was significantly more affordable and more flexible than previous systems. What many people don't realize is that Crew Dragon didn't just replace Soyuz for crew transport. It also quietly solved the very problem NASA had been trying to address with the Crew Return Vehicle decades earlier. In practice, Crew Dragon functions as an active lifeboat for the ISS, and in many ways it does the job even better than the dedicated rescue vehicles NASA once planned. We've already seen this capability demonstrated in several real-world situations. One example was the effort to return astronauts from Boeing's troubled Starliner mission when Crew Dragon effectively became part of the backup plan. Another example occurred more recently on January 15, 2026, when the SpaceX Crew 11 spacecraft brought 4 astronauts back to Earth after a medical incident aboard the station. These situations highlight an important point. Dragon isn't just a taxi to orbit, it's also a crucial part of the station's safety system. So the question becomes, why did Crew Dragon succeed where dedicated rescue vehicles like the Crew Return Vehicle never did? The answer comes down to how the spacecraft is used. Earlier concepts, such as the CRV or even Soyuz, when used purely as an escape vehicle, were essentially passive systems. They would sit docked at the station for months or years at a time, waiting for an emergency that might never happen. Maintaining a spacecraft solely for that unlikely scenario was extremely expensive. Crew Dragon takes a very different approach. Instead of sitting idle, Dragon is actively used in the crew rotation cycle. Every 6 months, a new Dragon spacecraft arrives at the ISS, carrying a fresh crew and replacing the previous vehicle. That means the station always has a recently launched, fully operational spacecraft docked and ready. One of the biggest advantages of Crew Dragon is that it's constantly being used and tested. A rescue vehicle that sits dormant for years can develop problems, batteries degrade, propellants settle, and software becomes outdated. Dragon avoids this entirely because its systems are exercised during every mission. Take NASA's Crew 8 mission as an example. After docking with the ISS in March 2024, the spacecraft performed routine thruster checks, sensor verification, and software updates during approach docking and departure. These procedures test Dragon's propulsion, navigation, and avionics in real conditions, while SpaceX engineers regularly upload updated software through the station's network. Another key difference is efficiency through multi-purpose design. Earlier rescue concepts, like the Crew Return Vehicle, were extremely specialized. They were designed only to bring astronauts down from orbit, not launch them into space. Dragon, on the other hand, does everything. It carries astronauts to the station, brings them home, transports cargo, and also serves as the station's emergency lifeboat. Because of this integration, NASA no longer needs to fund a separate rescue spacecraft program. Instead, the rescue capability comes built into its regular commercial crew missions. Cost is another factor. Crew Dragon is reusable for up to 5 flights, dramatically lowering the price per mission compared to single-use vehicles like NASA's X-38 prototype. And while the X-38 aimed for an advanced runway landing using a large parafoil Dragon relies on a much simpler and well-proven method: parachute splashdowns in the ocean, a technique used successfully since the Mercury, Gemini, and Apollo programs. Dragon also offers greater capacity and flexibility. The original ISS crew return vehicle was designed for 7 astronauts, while the Russian Soyuz capsule can carry only 3. Dragon was also designed for up to 7 people, although NASA typically flies 4 to leave room for cargo. That extra space can be crucial in emergencies. If astronauts from another spacecraft become stranded, a docked Dragon can potentially be reconfigured with temporary seating to bring everyone home. Another major advantage is SpaceX's launch cadence. Reliable rescue capability requires a system that can respond quickly if needed. Because SpaceX launches rockets frequently, sometimes multiple times per week, the company maintains a constant state of launch readiness. In Crew 11, the medical issue was identified 8 days before the crew's return. Finally, Crew Dragon includes several modern safety systems. One of the most important is its integrated launch escape system powered by 8 Super Draco thrusters. These engines allow the spacecraft to rapidly pull away from a failing rocket, even while still sitting on the launch pad. Earlier concepts like the X-38 did not include this kind of launch abort system. Instead, they focused mainly on returning astronauts safely from orbit once already docked to the ISS. Of course, Crew Dragon can also act as a direct escape vehicle from the ISS. In the event of a station emergency, such as a fire or depressurization, the spacecraft can autonomously undock and move away from the station even without manual control from the crew. That makes it a much faster and more reliable escape option than many older systems that relied heavily on manual procedures. However, there is one detail that sometimes comes up when people compare Dragon with NASA's old crew return vehicle concept. Dragon is currently certified to remain docked to the ISS for up to 210 days, while the X-38 CRV was designed to stay attached for as long as 3 years. At first glance, that might sound like a disadvantage. But in reality, the 210-day limit is part of Dragon's active lifeboat strategy, not a weakness. As said, because NASA rotates a new Dragon spacecraft to the ISS roughly every 6 months, the station always has a fresh vehicle docked and ready. If any component were to degrade, it would only remain in service for a few months before being replaced by a new capsule. The 210-day limit is also based on real engineering constraints. Dragon relies on solar panels and lithium-ion batteries, which slowly degrade in the harsh environment of low Earth orbit due to atomic oxygen radiation and micrometeoroid impacts. By keeping the spacecraft within this performance window, NASA ensures that if the crew ever has to perform an emergency return, the vehicle still has maximum power available for a safe re-entry. So technically, yes, Dragon cannot be left parked at a station for years the way the CRV was intended to be. But for the ISS, that limitation doesn't really matter. In practice, there are often 2 crew vehicles docked at the station at the same time, such as a Dragon and a Soyuz. When one spacecraft approaches its 210-day limit, its replacement is already on the way. And since typical ISS missions last about 180 days, the certification also includes a 30-day buffer in case the next launch is delayed. So in the end, the question becomes an interesting one. Would a dedicated lifeboat like NASA's Crew Return Vehicle have been the better solution, or does a multi-purpose spacecraft like Crew Dragon provide a more practical safety system for modern space stations? What do you think, Dragon or the CRV? Let me know your thoughts in the comments below. If you enjoyed this video and want to see more deep dives into space technology and missions, make sure to hit the like button, share this video with fellow space fans, and once again, don't forget to drop your thoughts